between 10 and 14 kilowatts into the system. So films have been created in both systems, the ECR system and the UHV system. The difference, you'll see what the difference is between the two. We have achieved high RRR in the UHV system on A-plane sapphire, of course, at 600 degrees C after an hour annealing at the same temperature. And the thickness was 600 nanometers that was obtained after 7 hours of coating at a pressure of 1 × 10⁻³ torr and a power of 60 watt. And the RRR result was it was 96 for this type of film. Now, I'll go to the ECR growth rate. We have achieved growth rates from 15 nanometers up to 135 nanometers per minute. For example, we had a 2-minute coating that yield 270 nanometer thick film at 120 volt bias. So we have already significant backsputtering at this point, and this yields to a RRR of 71. We also have achieved higher thicknesses, 4 microns without no bias, and 2 microns with a bias of 120 volts for a duration of 45 minutes of plasma. And here you can see some evidence of what Andre has been talking about earlier, which is that when you get to higher energy, you start to have significant backsputtering, and you end up having a trade-off between the incoming material into your substrate and what's leaving it. So in terms of adhesion, we even though we went up to 4 microns, we don't have a lot of problem with delamination for thick films. Even when there is an important lattice mismatch between the film and the substrate, like it is in copper and MgO. The only peel-off issues that we had, and this is going to go against what Enzo was saying earlier, is that we had some problems of peeling off or delamination, more exactly, of the film from its substrate when we were heating at temperatures higher than 400 C. And this is due to the roughening of copper. The temperature of roughening of copper for the 111 orientation is 400 C. So when you come up to that level, you start to have roughening of this of this orientation, crystal of this orientation, and you create steps onto your substrate that sometimes can be as high as the thickness of your film. So the film cannot delaminate from the substrate. So first I'm going to talk about the epitaxy of niobium on sapphire. Sapphire for sure is not the best substrate that we want to use for cavity, and most likely we don't want to use it for cavities. But it is a very suitable substrate to prove ground for niobium thin film study due to the fact that you have a low lattice mismatch with niobium, especially in the 1,1-20, which is the A-plane orientation, where you only have 1.9% lattice mismatch, which is much lower than, for example, 8.5% for copper or 10.5% for MgO. And the thermal expansion is comparable. So this is the type of structure that you can get. This is an SEM picture, and you have a fuzzy blowout over here. And this, if you remember the presentation of Josh earlier, you see those growth domain that he was talking about. And I'll keep on calling them growth domain. I refuse yet to call them twins until we have a proof. On the left, you have an EBSD pattern that shows you that this film, this is the scale 500 micron, and this is 1,500 microns, not 150. You have a single crystal film that has been deposited. Now, if I go to AFM images, whether they have been taken on films that have been sputtered under UHV or ECR deposited, you find again this kind of growth domain. This is for a film that is 50 nanometers thick, and you see here the same thing that Josh has shown on Monday afternoon, where you have this 6-pole symmetry, or basically you can see that you have 4 poles, and then you have the rotation of the 4 poles over here. Now, when you start growing the film up to 600 nanometers, this seems to start to fade away. If you go to a 4-micron film, for example, in DCR case, you end up with only the 4 closest neighbors, only 4 poles. So this is the film that has achieved a triple R of 96 that was produced under magnetron sputtering. So at the College of William and Mary, using the RHEED, they also try to look at the evolution of the strain as you grow the layer as well as its structure. So they can collect the images during the epitaxial growth of the niobium for varying thicknesses and growth parameters. Then with the MATLAB, they process the imaging, and they calculate the lattice parameter corresponding to the topmost layer of the sample using this equation for the lattice parameter, and they are curve-fitting the model. So what they have found is that this is the curve of the lattice parameter as a function of the film thickness, is that you start, if you think about bulk niobium, the lattice parameter is 3.3 angstrom, and you can see that you start here at very low thickness around this area, and the top surface actually you go in the opposite direction of a compressive stress in this case. And you see, and this is on the 111 direction. In the 112 direction, you see the same phenomenon. So, what are the what's the structure of these films versus the bias voltage, and which kind of results does that give? This is a table for films that have been deposited at different biases from 0 volt to 150 volts. One thing that I failed to mention is that at 0 volt, the ion energy that's incoming onto the substrate is about 56 eV. That was measured during gain phases. And you have the TC and the transition width, as well as the triple R. And you can see that we have achieved triple Rs of about 180 for different biases and high triple Rs. All the films, I only put one EBSD image here because they all look the same. They all 110, I'm sorry, films, and this one has been for the best film we got. And you can see that the grain average misorientation across the scan is only of 0.025 degrees. So we did these, we just got these results, and we have not yet found a correlation between the bias voltage and the triple R and TC yet. It seems that we have a trend, for example, if you remember the triple R curve that Larry mentioned, during his introductory talk, and see how you're supposed to, after certain energy, start to basically go down with the triple R. But this point is just pointing, making us lie, basically. And of course, these results, this is the first time we've done this work, and we have to repeat it. If we have at least to do it a couple of times to make sure that we are actually doing the same thing all the time. So this is for the same type of films, but with the substrate baked at different temperatures, 360 C, 700 C, and 900 C. And you can see that by baking the substrate at 700 C, we achieve a triple R of 213. Same thing, 110 orientation for about 1.15 micron in thickness. Now on this one, it only has a triple R of 71.5, but also the thickness is only 270 nanometers. As usually the triple R is depressed with a small thickness. Now, so this was for A-plane sapphire. What about C-plane sapphire? Again, this is an ACM image with a blow-up, and you can see again this growth domain, but this time at a different angle, which makes sense because what the face of the material that niobium C is different. And if you look at it, you actually can imagine looking at the cross-section of the C-plane and see the same angle. We also have look at 110 orientation on EBSD, but that's a more complicated story. Here, you have EBSD maps. This is the scale, 200 microns. So they all the top ones are 150 by 150 microns with a 1 micron step and different bias voltages, 0 volt, minus 60 volt, and 150 volt. And you can see that we have a shift from orientation of 111. You can see the IPF pole figure for the color-coded map over here, where we have pure 111 orientation, but when we go to a higher bias voltage, we switch to 110. Same thing here for at a finer scan. So, and when we go to, for example, if we go to 150 volts, you also have, you see that here that you have the 110 orientation with the different growth domains, but you also have part of it is a 111. This it's an XRD. XRD pole figures and the Bragg-Brentano corresponding to it, where you can also see the 222 niobium and the 110 niobium peak. So in the case of C-plane sapphire, as a function of the bias, you can achieve different TCs. And again, we don't really see a trend yet in these, and we have to do much more analysis to actually get conclusions. But you can see that we can also achieve on the C-plane, which is a worse lattice match for niobium of 108. And these films have all been coated at 360 C after a baking at 360 C for 24 hours. So a partial conclusion for the epitaxy of niobium on sapphire, all the A-plane, all the niobium films that we have grown on A-plane have shown a 110 orientation, both for the magnetron spotted film as well as the ACR film. And the niobium films that were deposited on the C-plane sapphire actually switch from a 110 orientation to a 111, switch to a 110 orientation from a 111 orientation. And if you remember the wild sketch that I showed you earlier, what you anticipate is actually the 111. But I'll direct you to this reference that shows that for MBE niobium film that have been grown on C-plane sapphire, they are actually, they grow as along the 111 or at 900 C, but when you go to 1100 C, they start going on the 110 orientation. So just as a partial conclusion, we have actually achieved triple R values that go from 8 to 213 just by varying the incident energy as well as the bias voltage, with the bias voltage as well as the temperature. So that shows that we can probe different quality of the film for the according to the parameters. The only thing that, of course, triple R tells us is that the quality of the film, because there's so much contribution to it that by no way it will going to give you the RF behavior. Now I'm going to go quickly through the niobium on MgO. You see here again with the SEM picture that you have the same kind of growth domains, but now it looks like cubic, which makes sense because MgO is on an FCC material. So this is same AFM pictures on the for films that have been grown with magnetron sputtering, where you see also on the right the same behavior. Now, when you grow it with ACR, you get the 110 orientation. Over here, you have a 60-degree angle. You see some domains that actually varying of an angle of 60 degrees at a higher bias. Okay, for a bake at 700 C and coating at 360, we obtain a triple R of 115. For a micron, it's about 1.3 micron thick, and that just show you that even with a lattice match that is of 10.5%, you can achieve higher triple R or a good quality of a film.